Hi, it's Jean at Flamingo Math. This is lesson 6 in Unit 13 on our statistics, data analysis and statistics for Algebra 2. We're talking about confidence intervals and hypothesis testing in this final lesson. A confidence interval is an estimate of a population parameter, and we usually state it as a range with a specific degree of certainty. The most common are 90%, 95%, and 99% confidence intervals. And you find the confidence interval by taking the average, the mean, plus or minus the error. And we'll look at those formulas in a little bit. So these are all the vocabulary terms and formulas that could be used in this lesson. So the confidence level refers to the percentage of probability or the certainty that the confidence interval would contain the true population parameter when you draw a random sample many times. So we need a large sample and it's got to be random. And here is the standard bell curve showing where 90% of the confidence interval lies, then 95%, and then 99%. We're going to look at getting these values down here next. That's called the z-value. It corresponds to a specific confidence level, and it's called the critical value. So you can see from our chart that these values were already placed in there for us. But you could use any confidence interval, excuse me, you could use any confidence interval, and if you needed to calculate one, we need to know a formula or a method for doing that. So let's just consider first the 90% confidence interval. You find that by taking 1 minus the confidence and dividing that by 2, since half of it is on one side and half on the other side, or in the tails. And then you want to find the inverse normal. Now I put the keystrokes for the TI-84, but I'm using a TI-Nspire here, so let's walk through that. You can see on my screen here that I did 1 minus 90% cut in half is 0.05. And then I want to do menu and statistics and distributions. And number 3 is inverse normal to find that tail. So my confidence interval is 0.05 for 90%. And we'll say okay to that. And you see that on one tail it's 1.644. So going back to our graph, 1.645, you can see it's negative 1.645 on the left, positive 1.645 on the right to get a 90% confidence interval. So if you needed to figure an 80% or a 75%, that would be the method to do that on this page here on this slide. So oftentimes we want to find the maximum error of an estimate, and the maximum error of an estimate, capital E for a population mean, is given by this formula where I find the z-score, the z-value, times the particular confidence level, that's the standard deviation of the sample, and divide it by the square root of the sample size, providing that the sample size is 30 or greater. So here's an example of that. Let's say you have a poll of 214 randomly selected high school students showed that they spend an average of 16 minutes every day on a social network for sharing user-generated videos. So that sounds like TikTok or Snapchat or something. And there's a standard deviation of 2.8 minutes. And we want to use a 95% confidence interval to find the maximum error of the estimate for the time spent on the site. So our formula said that the error is the z-value times the sample, the standard deviation, divided by the square root of the sample size. and we want 95% confidence. So without figuring it ourselves, we'll go back to the table here. We're going to use 1.960 for our z value. And the standard deviation, S, is 2.8. This is our standard deviation. And the sample size was 214 students. So the square root of 214. And we want to calculate that to see what our error is. Look. So we've got 1.960 times 2.8 divided by the square root of 214. So we got a 0.375. Whoop. And again, if you wanted to calculate that z value for yourself, you could do that by saying 1 minus 95% confidence cut in half would give you 0.25, and then you would calculate the inverse normal. I'm going to move this around here. Then the inverse norm would be negative 1.95996. So we could check that out. Menu, probability, or statistics, distributions, inverse normal, 0.025, and 1.95996 is our z value. So I just rounded up there. And the error was about 0.375. So we need to explain what that means to our findings. So we could say that you can be 95% confident that the population mean time spent on the video website will be within 0.375 of a minute of the sample mean of 16 minutes. The sample said they spent 16 minutes. So putting that into words, you can be 95% confident that the population average time or population mean time spent on the site video website will fall within 375 of a minute. So just a few seconds, right, of the sample mean. And the sample mean was 16 minutes. So you could figure it's either going to be 16 minus 0.375, so it would fall between roughly 15 and a half to 16 and a third. So somewhere between 15.625 and 16.375 minutes that they spent, roughly. Okay. So confidence intervals, here's the formula for confidence intervals. A confidence interval for a population mean is given by this formula, where x bar is the sample mean and e is the maximum error, or by using that maximum error formula right here to calculate the e value, the estimated error. Oh, what happened? I missed something. So example 3. A sample of 200 high school teachers was asked the average amount of time they spend outside the classroom on school-related work. The mean time reported was 16.6 hours per week with a standard deviation of 2.7 hours. And we want to figure a 99% confidence interval for the population. And we just said the confidence interval is the mean time, which is 16.6. So x bar plus or minus the error. And the error was the z-score times the standard deviation divided by the sample size. So this confidence interval is going to be 16.6 plus or minus, let's see, what was the 99%? So looking back, 99% is 2.576. 2.576 times the standard deviation, that's 2.7 hours, divided by the sample size, so the square root of 200. So let's just figure out this error here first with the 2.576. Whoop, that didn't work, did it? 2.576 times 2.7 divided by the square root of 200 teachers. So 0.4918. So we got 16, oh, there's my number, 16.6 plus or minus 0.4918. So our confidence interval is between 16.6 plus 0.4918 and 16.6 minus 0.4918. So somewhere between 1611 and 1709. So let's write it in a sentence here. We can say the 99% confidence interval is 16.11 mu to 1709. And this is in hours. So you can be 99% confident that the population mean time for teachers who work outside of the classroom grading papers is between 16.1 hours and 17.1 hours. That's a lot of hours outside of class. Okay, hypothesis testing. When we want to estimate the population mean, we've used a confidence interval. But if we want to assess a specific claim about the mean, we have to use a hypothesis test. So two different things are happening in this lesson. We're looking at population mean, and we're looking at making a claim using a hypothesis test. And there's two parts to a hypothesis test. There's the null hypothesis, which is a statement of equality when something's equal to something that we're testing. And then there's the alternative hypothesis. So it's the ho and the ha. And the alternative hypothesis is the inequality statement, and it's the complement of the null hypothesis. And a claim can be part of the null hypothesis, or it can be part of the alternative hypothesis, just depending on how you word a claim. So here's 3 examples for us. You have a business owner who thinks employees spend more than 90 minutes per day surfing the internet during work hours. So do you hear the inequality? More than, that's the the alternative hypothesis, because it's a statement of inequality. They're saying that the mean is more than 90 minutes. This is the claim. So the null hypothesis would be the equality, and that would be when mu is less than or equal to 90. So I got the claim from the words more than 90. That's my claim. In part B, Mrs. Sharp believes she works at least 8 examples every class period. At least. So you need some equality there. That would be the null hypothesis, or the HO statement, where the mu is greater than or equal to 8. At least 8 examples. This is the claim. And then the alternative, or the HA, would be mu is less than. So Mrs. Sharp works less than or fewer than 8 examples. And then the last one, Emily thinks it takes more than 10 minutes to drive to school each morning from her house. So this is like the first one in part A, which is the alternative hypothesis. It's an inequality where mu is greater than 10. That's our claim. And the null hypothesis, O, is mu is less than or equal to 10 minutes. Okay, next we're looking at significance tests. So these are z-tests because our samples are bigger than 30. So a z-test is the type of hypothesis test we're using. The k value represents the claim about the population mean mu. So we have a left-tailed test if mu is less than a k value. We have a right-tailed test if mu is greater than a k value. And we have a two-tailed test when mu isn't k. And the test for a hypothesis testing, we want to state the hypothesis and identify the claim, determine the critical values in the critical region, calculate the z-score, and either reject or fail to reject the null hypothesis. In that procedure, then we can make a conclusion about the claim. So let's look at a few of those. Oliver thinks there are more than 8 commercials during a 30-minute program. Using a sample of 45 programs, he calculated an average of 8.5 commercials with a standard deviation of 1.8. And we want to test the hypothesis at a 1% significance level. So in our procedure, first we have to state the hypothesis and identify the claim. So the claim is an inequality that mu is greater than 8, more than 8 commercials. This is our claim. And the null hypothesis is that mu would be less than or equal to 8. Next, we have to calculate the critical value and the critical region using the z statistic. So that would be x bar minus mu. So x bar is the average, that's 8.5. 8.5 minus 8. And then we're dividing by the standard deviation, that's 1.8. divided by the square root of the sample size, 45. So we said that formula was x bar minus mu divided by s over the square root of sample size, the standard deviation over the sample size. That's our z statistic. So let's do that calculation. 8.5 minus 8 is a half, and we're dividing that by 1.8 divided by the square root of 45, which is 1.8633. So our z statistic is about 1.863. Now, when you consider the bell curve, and we wanted this area here, 2.576, and our z is 1.863. It's over here somewhere. So 1.863 is less than 2.576. So that means the HO, or the null hypothesis, is not rejected. There's not enough evidence to support his claim. Wait, I need to say not enough. Oh, O's not rejected. There's not enough evidence to support the claim of more than 8 commercials in that 30-minute primetime program. It's got to fall within this range to reject the claim, to reject the null hypothesis. Okay, 2 more to go. A food label states that there are 150 calories per serving of your favorite cookie. We're using a sample of 40 servings. You calculated a mean of 150.8 calories with a standard deviation of 2.1. And we want to test the hypothesis at a 5% significance level. So the null hypothesis is that the claim is there are 150 calories. This is our claim. The alternative is that mu isn't 150. So now we're talking about, this is a two-tailed test. We're going to look at a two-tailed test. The mean was 150.8 calories. The standard deviation is 2.1, and the sample size is bigger than 30. The sample size is 40. So we're looking at a 5% significance. So that puts us at negative 1.96 and positive 1.96. So we're thinking about this tail and this tail in our hypothesis test. And we need a z-value, so that's 150.8 minus the claim 150 divided by standard deviation over the square root of the sample. So we'll do that calculation. 150.8 minus 150 is 0.8 divided by standard deviation over the square root of the sample size. And that's 2.4. So what happens in this case, our value falls over here, 2.4, within that shaded region. So we have to reject the HO. Or the null hypothesis. The z-value falls within the critical region, Ho is rejected. Z value falls within the critical region. The claim that there's 150 calories in every serving of cookies is rejected. The claim that there are 150 calories in every serving of cookies is rejected. Okay, so our Z value has to fall within that critical region, and then you can reject the claim. The last example, we have a soda manufacturer claims that there's 12 ounces of natural juice in every sparkling berry fizz. So that's our claim. When it's an equality, that's the null hypothesis, that mu is 12. This is our claim. So the ha is that there is not 12 ounces. Again, when that inequality happens, we're talking about a two-tailed test. If we use a sample of 65 cans, that's our N value, Jeff calculated the mean to be 12.2 ounces with a standard deviation of 0.95 of an ounce. That's a lot going over. That's almost a full ounce. We want to test the hypothesis at 1%. So 1%, that's 2.576, right? So 99%. So we're looking for our data to fall in a two-tailed test, either over here in the 2.576 or over here in the positive 2.576 to get 99% significance. So we need a Z value. That's X bar minus the claim over standard deviation divided by the square root of the sample. Let's see where that falls. So 2/10 divided by 95.95 over the square root of 65 gives us 1.6973. 1.6973. So 1.69 falls in here, 1.697. So 1.6973 is less than the 2.576. Doesn't fall within that tail. So the ho's not rejected. Because the Z value does not fall within the critical region. The critical region, there's not enough evidence to reject the claim of 12 ounces of natural juice in every can. There's not enough evidence to reject the claim of 12 ounces of natural juice in every can of sparkling berry fizz. So we can be pretty sure that there is 12 ounces. of sparkling berry fizz. Okay, that's the end of chapter 12. Thanks for joining me. See you next time. I meant to say chapter 13, not chapter 12. This is the last chapter. Bye.